Yeah, I think it's time for us to start the lecture. So this is the last lecture on the theory of this course. So yeah, this is the last lecture with me, also with you. And you will hear update from Roy or Yoga. Yeah, just want to share with you that we have uploaded previous year's exams on the Blackboard, and you will see example question from the DC motor, induction motor, PM motor, and also we have a lot of numerical calculation. And we have also uploaded the solution there. So you can, do some practice on those numerical calculation. So in the lecture here, we don't focus that much on the numerical calculation, but maybe from next year we'll try to include also them some numerical calculation, so it might be easy for you to understand. But anyway, when you are working on those example on the exam question, and if you have any question, just drop by in our office, knock the door, and come and discuss. Or you can also write us email, and then we can make an appointment. Then we can discuss there. So that's the one thing that I want to share with you. And then I will start the induction machine, the last part of the induction machine. And I will start with a little bit repetition from the last lecture. The main modeling part that I want to discuss here, what we see first, we have the two axes. One is the alpha axis, is the alpha for stator-oriented model, and then you have the beta axis for the stator-oriented model. And then we see the voltage for the stator, US. We put also S in the superscript, and it's a vector. And then we see that it is RS, IS, plus d psi S, dt, something like this. Since it's in per unit model, then you also get 1 over omega n here, that we can write here. So this is the stator voltage, and of course it's in a stator oriented frame. And then we also see that for the rotor, and we have the rotor axis here is alpha r, we put r, and then we have beta. So we have beta r here for the rotor. And also we check rotor voltage, and we saw it, UR is a rotor frame, and then we have RR, IR plus 1 over omega n d psi r dt. Okay, I put their space vector here, or they are in phasor or vector. So this is what we see, and we also see that there's an angle phase between these two, and we're saying that this is theta, this theta. And then next step, what we did, we converted the rotor-oriented frame into a stator-oriented frame. So if we convert them into a stator-oriented frame, a stator-oriented variables, then what we did, we changed this variable, this d theta, into d dt minus j n, and this n is d theta over dt. That gives us the n here, speed of the rotor. So then what we see, the stator equation, the rotor equation, now we got the new rotor equation. I can write the new rotor equation here. Is the new rotor equation, and it's now a stator-oriented frame, which we got RR, IR, now it's a stator-oriented frame, plus 1 over omega n d psi r is r here. And now it's stator-oriented, minus J in psi r, stator oriented frame. So what we did, now we changed this direction, put it to here in the stator oriented frame. We converted it into here. This is the first step now what we did. And we are also saying that this two in the alpha beta frame, this means they are fixed in their position. These two axes, alpha S and alpha R axis, they are fixed in their position. And then next what we do, we try to find another axis. Then we put the name, it's alpha K. And then we also say we have the beta K. And this alpha K, later what we see that we oriented it into rotor flux direction. This is the rotor flux, direction of the rotor flux, we oriented it. And also we see that it was rotating with a frequency of Fs, something like that, or maybe Fk, you can say. It was rotating with a frequency of Fk. Previous two, alpha S, alpha R, they are fixed in their position. Now we define the new vector. It's alpha K, and it is rotating with a frequency of Fk. In some article on some books, you'll see them defined as a D axis or the Q axis. Since they are rotating, when this vector they rotate, this axis rotate, then we call the dq domain. But in this course, we represent them like alpha K and the beta K. In some places you see D and Q. So when we converted them to dq, now you have these two equations. The first one and the second one, these two. Yeah, one thing you can see that here we change the angle to this direction. Now we are putting it to this direction and it's rotating. If it's rotating in that direction, the counterclockwise, then the derivative term here, we can represent this derivative term dt, which is plus j f of s or f of k. So now we have them into new frame, fk, or later we see that it's a, or maybe f c r. Since it's a rotor, we can write the rotor frequency or fs, whatever, or fk. Then you will see that you got the new equation for the stator, and which become us, now is k, and rs, is k, plus 1 over omega n, d psi s, now is k, plus j of fk psi s, okay. So we got the new quantity there. And also for the rotor, we got the rotor, now is in the k, and now we have the rr, irk, plus 1 over omega n, d psi r k dt. And here you can see, before we have this minus n, now we have also plus fk, then we can write it j of fk minus n psi r k. Now we got them in the new axis, new orientation, in the alpha k orientation. And one thing is different. When we present them in a stator-oriented frame, they are still AC quantities, alpha, beta, sinusoidal quantities. But now in the new frame, alpha k, and we are saying that alpha k is rotating. So now we got these two new equations here. These are the two new equations. And here the variable in the rotating frame, and they are DC quantities. So now we got the new variable, they are in DC quantities. So that is what we did in the last lecture. So we come to this part now. So we are now interested about the steady state operating condition of the machine. And if you want to look at the steady state operating condition, then what we do, we put the derivative part to 0. So you have one derivative part here and another derivative part here. And now we put these two derivative part to 0. And then you get the steady state equation. So here we got the steady state equation, two steady state equation, one for the stator and one for the rotor. And also we put the rotor voltage to 0 because it's we are considering it's a squirrel cage induction machine, and we see that the bar in the both side, they are connected. This means they are shorted, so no voltage there at the end. And one thing I forget to mention here in the model that we developed, here you can see the frequency difference here, the speed difference, Fk minus Fn. And then we define this to Fr in the model. So it's Fr, which is Fk minus N. Here, N is the speed of the rotor, and Fk is the rotation of the space vector. And also later we will see that if this Fr is 0, then there is no torque. Torque is 0. So in order to produce torque by this machine, squirrel cage or the induction machine, there must be some speed difference between the stator voltage frequency and the rotor speed frequency. So there should be difference. And then if you have there's a difference, then you will get torque. So that's one important thing to remember for now. And there must be. And why there is no torque? Because you can see that if we look at the coil in the winding, in the, let's say this is alpha winding, and then we have this squirrel cage bar there, and which are shorted. We have this flux there, and if this bar, they rotate at the same speed of the Fk, they're rotating the same speed of the Fk. If they're rotating the same speed of the Fk, and you'll see that there is no change of flux in the rotor bar, since they're rotating the same speed of the stator flux. So since they're rotating the same speed of the stator flux, so there will be no flux change in the rotor bar when it rotates. This means there will be no current induced, because no voltage will be induced, because there's no change of the rate of change of flux. So therefore, we got 0 torque. So that's the important thing that we'll see that to get the torque, we must have, there's a difference between the speed, the frequency of the stator flux and the speed of the machine. And if you remember the machine modeling, or when you have the machine course, and that time we are not talking about the drive. We are just connect the machine directly to the AC power supply. So in that time, we define the slip. That is the difference between the grid frequency and the rotor frequency. But here now we are providing through converter. And we have the capability to regulate the frequency, voltage, whatever we want, to have the desired frequency, desired torque, desired speed. So that is the advantage. So now we have the steady state equation. And we are saying that they are now in the rotating coordinate system. This means that we oriented them for now, let's say, a rotor flux vector, and it's rotating with the speed of Fs. So therefore, we have this Fs here. It's rotating with the speed of Fs, and then we have this steady state equation. Now we are interested to look at the steady state behavior of the machine. Yeah, when it's running steadily, and then it is an operating point, then we are interested to see the behavior. So in order to see the behavior, we do some trick in the equation. Yeah, to do it so that we can understand the behavior. For now, for example, if you see these two equations and there is no link, direct link that we can represent in terms of the circuit. But if we do a little change, then we can have them a kind of a common connected circuit. So what we did, we inserted the psi S and the psi R, these two here in these two equations. This is the first step, that's what we did there, inserting these two equations. And then in the second step, we also did that to have the sum, we apply some trick. We multiply the second equation with this Fs over Fr. And when you do that, and you will see that these two equations become a very nice equation, like this, when you do that. So we got two very nice equations, and one thing is common there, this part. So we see that this part is common, and here is multiplied with this magnetizing current or the mutual current here, this magnetizing current. So now we can easily draw the circuit. It's in a steady state condition, and also they are in rotating coordinate. This means all the variables now here, they are DC quantities, not anymore sinusoidal quantities. So they are DC quantities, and what you see here, we have in the first equation, input is the stator voltage input, and then you have the drop across this resistor and this inductor, this leakage inductor, that you put the resistor and the leakage inductor and current IS flowing there. And then second part, for now maybe you can forget this part. So we don't need to remember this part for now, only the first part. So we inserted the first equation here, and you are saying that the current IS flowing there and current IM flowing here. So that's how we can represent them in the circuit. And now we want to look at the second equation, stator equation, and we see that this part is common there, this the mutual part, magnetizing part is common, then we kept it common. And then we have the second part. This one is the drop across the resistor, and another drop across the reactance, leakage reactance, that we put both part on there. So now we have the circuit, and now we can easily analyze, even though we cannot measure the current in the rotor, because rotor is rotating, is a squirrel cage, then it's not easy to measure the current, voltage, anything there. Voltage is 0, but it's not possible to measure this thing. But now somehow we can measure the rotor current from here, from this equation. Since this variable, resistor, inductor, all these things, they are measurable. If you have any machine, and then you can find the value of this of those quantities, all this, but not the current when it operates. So now we have the circuit equation, simple circuit equation, then we can analyze it. That's the one good thing that we have. It's also possible to represent the circuit a bit nicer way. This is the classical way of representation, but it's also possible to present it a bit nicer way for the rotor flux linkage equivalent scheme. Then we see that we are even able to remove this leakage inductance from the rotor circuit. So what we did there is the same equation that we have in the previous equation, previous circuit, not this one. Here, first we inserted the psi S and psi R, and then we have this XX here. You can put this XS is equals to X sigma plus XM. This is the one thing that we do. And then we also know that magnetizing current, this IM, which is possible to write like IS plus IR. That's also possible to write. And there we also write that IMR, this is the magnetizing current of the rotor, is also possible to write it that we see before, which is IS plus 1 plus sigma R IR. So those are the equations that we already developed previously and inserted them to this equation, and then rearrange them, and then you will find these two nice equations here for both the stator and the rotor. We set a reference, I think, in the compendium. So if you're interested, you can go detail, but I don't think it's necessary for you. and we will not also ask you in the exam to derive this equation. But it's okay to see that we got these two nicer equation for the stator and the rotor. So now you have these two nicer equation for the stator, then you can use this equation to analyze the behavior of the machine. So first, maybe I will present the discussion for the first circuit. And in the first circuit, what you see, so we see that we have the three flux. One is the stator flux, rotor flux, and the magnetizing flux. And if you look at where they are, and the stator flux is here, right? This is the stator part, CS here. And the rotor one is here, CR. And then we have the magnetizing one, CM, is here. So, yeah, the flux that we know that is the flux is the like US. If you neglect the resistor, then US you can write the like J, F of S, CS, right? So if you know the voltage, then you know the flux there at this point. So you have the current, stator current, and the rotor current from the circuit, and if we try to find the relation between the flux, then you can find the relation as a circuit parameters. So we can try to find the relation between these two flux, between these three fluxes, and then you will see that they come something like this equation. The first one is this magnetizing flux, which is in terms of stator flux. So you don't need to derive all these things, but for now it's okay that we got this relation. There's enough that we can get some relation, and this relation comes from the circuit equation. So we want to investigate, if we want to keep the different fluxes constant, then what will happen? Like in the first one, we are keeping the flux here, and we know that the stator flux, which is here, we can write like a short form, like J of F of S, CS, and then you are getting actually CS, which is US over F of S. So if you keep this stator flux constant, what will happen when the loading is increasing? This means we are increasing the current in the circuit. This means the other two fluxes, they are reducing. In the first one, we keep CS constant. If we keep this CS constant, and you see that the other two fluxes, is the CR and CM, they are reducing when you keep this part is constant. That is the one thing that what we see from the circuit. Because we are increasing the current, but we are keeping the ratio the same here, constant. And then you'll see that the other two is reducing. In the next part, if you keep CM constant, then what is happening? If you keep the CM constant, and you'll see that the CS it's increasing and the CR is decreasing. So is all this, the relation that I'm discussing is coming from the circuit, and based on the relation that we develop, and if we plot them, yeah, we can use the MATLAB or anything to plot this with respect to the loading FR. FR is the loading or increasing the current in the machine. So what do you see in the first step? You are keeping CS constant, stator flux, and if you keep stator flux constant, and you define which one is what, this one is the dashed line is for the rotor flux, and the dash dot is for the magnetizing flux, and you can see that if we keep this one constant and the other two reducing. So we see a similar behavior. And when we keep the magnetizing flux this constant, and what you can see, if you keep that one constant, and then you see that this rotor flux, this is the rotor flux, is reducing while the stator flux is increasing. So when we develop the control method, and we see that this is not this method, keeping CM constant is not a good method, but we can try the other two methods, like keeping stator flux constant. This is the one method that you can use to control the machine. The other method is keeping the rotor flux constant. So you have the rotor flux constant, this one, and you see that when the rotor flux constant, both of them increasing. Stator flux is increasing very high, and we don't want the machine to be saturated. So therefore, we keep the stator flux, rotor flux, something like maybe 0.9. If we keep it 0.9, something like that, then we are limiting the stator flux also. So the machine will not be over-saturated. So this is what we see from the steady-state characteristics of the machine. Any question here? So now we have this classical model. Yeah, this is the previous one, classical model. And from the classical model, we see that we are considering, we have three scenarios. One is the keeping a stator flux constant, and the second scenario is keeping the rotor flux constant, and the third scenario is the magnetizing flux constant. So the first one, we can check with the stator flux constant. What is a stator flux constant means? We know that already. Stator voltage, which is US, and you can write it like, is here. You can write this US, something like this. If the resistor is very small, resistor is already very small. I mean this stator resistor is only 1-2% of the in per unit. So that's very small. Then we can write the stator flux. We can get the stator flux, which is the ratio between the frequency, between the voltage and the frequency. So when we have the converter, and we can control the voltage, output voltage of the converter, and we can also control the frequency of the converter, and we keep the voltage and the frequency ratio constant. That gives us the constant stator flux in the machine. So now we got the constant stator flux machine. And for that, if we derive the torque equation, and you will see the torque equation become like this from the classical model of the machine. So we got the torque equation. Yeah, there is a lot of a step to derive this equation, but it's not important for you how to derive. The important thing is that we got this equation. That is the important, and how this equation behaves. That we want to look at. And I also want to mention another thing here. The frequency, this term here. So when the frequency is very low, and you can see that this term is small, since the frequency is low. And this term depends on the frequency. Since the frequency is very low, and then this term, the resistor drop across the resistor also become very high, it's dominating, because the frequency is low. If the frequency is high, then the drop across the resistor is very small, you can neglect it. But when the frequency is low, then this effect, it has a very big effect. So when you design the control, we also need to consider that effect for the low frequency, like this one here. So we derive the equation for this, and we are calling them resistor compensation, RS compensation. So we need to do this RS compensation for the low frequency, because when the low frequency, we see that this part is dominating, and we don't want that, because we want to have the constant flux. In order to have the constant flux, so we do some trick so that the effect of this component can be compensated. The resistor, we call it RI compensation, or only resistor compensation. So when we do the compensation, or at the high frequency, then we got this, and this torque comes in terms of this frequency, rotor frequency. And we know that this is the difference between the stator space vector minus the rotor speed. So we have this, and then how the behavior look like then? If you plot the torque in terms of the speed, and then how it look like? I think you are very familiar about the torque characteristics for this, which is something like it goes and then it has the maximum pull-out torque, and then maybe it would be a bit more steep. It's symmetrical around this point. So you can see the torque, torque speed characteristics. This is the speed of the machine, and this is the torque here, and we have the pull-out torque here. So if you plot the equation that we have here, the torque equation, and you see it's something like this. It's in terms of the speed. So that's what we see, and we have this maximum pull-out torque. So when we keep the stator flux constant, we got the characteristics of the torque, something like this. So if we want to run a pump load, and what would be the behavior then? You can plot the characteristics of a pump load. Maybe it would be like something like this. This is the torque of the pump load, it is speed. And we know that according to Newton's second law, and we see that this is the swing equation, that's what we have, which is TL. No, I think it's TE minus TL. So what do you see here in the beginning? We have the electrical torque. This is the electrical torque characteristics, and we have the mechanical torque, the pump load torque. And we see that electrical torque is much larger than the mechanical torque. So we see that this one is much larger than this, and then we see the acceleration. So this means it will continue to accelerate, increase the speed. So it will continue increase the speed, and when it reaches to this point, we see that both torque are the same. So at this point, both torque are same, this point, and it settled down to this point. So this is the speed of the, this will be the speed of the machine, there, rotor. And let's say this is at this point, it could be a stator, rotor flux vector, something like this, stator flux stator frequency. So from this torque characteristics, what do you see? That we have this Fs here, and when the speed of the rotor reaches to this point, and the torque is 0. So therefore, we need to have always Fr with some value, which is Fs minus n. As long as you have this Fr, there's a deviation between these two frequencies, and you'll get some torque, and they look like this. And when we operate a machine, then we usually operate in this region. So this is the reason that this symmetrical region where we operate machine, and here is a motor application, and then it's the braking or the generator application. That's what we do. So we are talking about the rotor flux constant. So we are talking about the rotor flux constant, and then if we start with a small, maybe I should also say one more thing. If we change the axis here, like we have the axis now at this point, this is the axis point now, and now we change the axis to this point here. Now we got the new axis here, torque, and then instead of n, now we put it here, Fr. And then how it should look like, if you put instead of n, now we put it Fr there, and then you will see that it would be something like, something like this here. Maybe not like this, since Fr is positive here. So it would be something like this. So you have Fr, and here it is torque, and this is Fr we have. So as long as we have some Fr, and then we'll have torque. So this one we can now, instead of n, now we're presenting is Fr. So Fr is the difference between these two, speed, and When Fr is 0, this is the 0 point, and the torque is 0. When you have Fr, then we will have torque, then we come to a maximum torque, is the pull-out torque of the machine, and we got the pull-out torque. So this is the behavior that you can see from the classical machine modeling. This for stator flux constant. So when we start the machine, and we don't put all the voltage at a time from the converter, we slowly increase the voltage of the from the converter. So when you increase the voltage slowly, then how it look like? Since we want to keep the stator flux constant, then we try to increase slowly. Like here, you have the Fs, the ratio, 0.2, 0.4. Then when you have the low stator flux, and then you can see that we have the torque characteristics is this one. Because we have a lower stator flux, and then you can see that we get the pull-out torque here. And when we increase the stator flux, 0.2 to 0.4, then you got this one, and it's increasing. According to definition or according to formula, that we see that it should be something like the same, the pull-out torque. But since we have the resistor drop, therefore we are not getting the same for this one. We are getting when it's a 1, the ratio when it's 1, then we are getting this curve. But when it's less than 1 stator flux, we are getting like this. It's a bit lower because this is the drop in the resistor. So it's up to the speed 1 per unit. And when you want to operate the machine higher speed than the rated speed, then you need to do the field weakening. So we try to reduce the field of the machine, and then when you apply the field weakening, then we see that the maximum torque that you can have now they reduced. So this is the one characteristic that we are talking about, the rotor flux constant. And then we are also see that it's also possible to have the other flux constant, like the, maybe I should also say that you would see this constant UF control in many applications. It's widely used in industry, this UF control of an induction machine. This is one of the very popular method used in industry. And then another method can be the rotor air gap flux control, keeping the air gap flux constant. And if you derive the torque characterization, if you find the relation between the flux linkage, air gap flux linkage and the torque, and you'll see like this, and you can see that it's more like the similar as the previous equation. And if you draw, and you'll also see the similar torque characteristics, like the one that you have seen for the other one is Fr and the torque. So you'll see similar characteristics, but like this, similar characteristics as the previous one. The one thing is that here we see that when we increase the loading and you want to keep the magnetic flux constant, then we see that rotor flux they reduce and the stator flux increase for this condition. So therefore, we don't use this one that much, but it gives something like this. Any question here? Yeah, in this course, we mainly focus on the rotor flux constant control. This is the one very popular method, rotor flux control, constant, keeping the rotor flux constant. And then if we are always interested to find the relation between the torque and the flux, and we will come up the relation that the torque is a square of rotor flux linkage, and it's the linear relation with this Fr, the speed deviation, speed difference between these two. So we see that this is a linear relation between torque and the Fr. But the previous two, they are not linear relation, and they are like this, right? The torque and the relation, if you look at the relation, and they're not the linear. Therefore, we got that type of torque, that type of the torque characteristics. But here is the linear relationship from the constant rotor flux. So what does that mean, the linear relation? This means if you increase this, you are getting the linear torque curve. So I mean, there is no limit. This means there is no pull-out torque. For other two, we see that there is some limit that they stop in somewhere and then coming like this. But for this one, it is linear. It's going increasing. So there is no torque. There is no pull-out or maximum torque for this one. So what we do at the lower speed, we keep flux constant, rotor flux constant, and then when you apply this control at the lower speed, we keep the rotor flux constant, and when we need to operate higher than the nominal speed, then we do field weakening. So we can do the field weakening to have the higher speed. So this is the torque characteristics that I'm talking about. And in Y, we have the torque, and on the x-axis, we have this FR. And of course, this FR, which is Fs minus N. And what you see here, when you have the stator flux constant, and you have the sum, it is somewhere here, getting maximum, and then it's coming like this. It's going max, and then it's like this. Yeah, since we did not plot all this thing, and it will be like this. And if you look at also air gap flux constant, then it will also be somewhere the max, and then it will go somewhere like this. But for the other one, and you'll see it's going, yeah, like this. So there is no pull-out torque. So this is the characteristics that we can see, yeah, based on the classical model of the machine that we derive. Any question here? So the most important thing that for you to understand the concept. Once you understand the concept, then when you work in the real drive modeling, drive development in the software, then you can implement the logic there, program, to have all the functions that what you want. So therefore, we focus on mainly on understanding the concept of the machine modeling and how to control all these things. Once you understand this thing, and those are just equation in the software, in the FPGA. If you look at the 50 years ago, then it's only the operational amplifier. That's what we have. And we need to, it's not that easy to implement all the mathematics equation in just using operational amplifier. But now we have the microcontroller, all the DSP, digital signal processor, and then we can implement all the sophisticated control with a lot of programming. And then now we have the FPGA, field programmable gate array. And then we can even implement even with a higher resolution, with a megahertz frequency, very small time, sampling time. So now, yeah, we can think many different control for the motor drive application. So you have a few seconds before the break. If you have any question, then I can take the question. Yeah, otherwise we can have 15 minutes break, and then I will continue after the break because I want to finish the lecture today so that you don't need to attend the theory lecture from next week. Yeah, so we can take 15 minutes break now.